and welcome to the Role Model series. Here we talk with some of the brightest minds in astrophysics. Real conversations about their work and what life as an astrophysicist is really like. These quick 30-minute interviews will give you a glimpse behind the scenes. So, let's get started. Today, we are joined by Dr. Navin, a postdoctoral scholar at Stanford University. His research deals with extreme environments around black holes and neutron stars, exploring phenomena like fast radio bursts. I'll begin with the first question. Looking back at your childhood in Tamil Nadu, what were your childhood dreams? And for you, what was the moment that sparked your path towards astrophysics?
I don't think there was any specific discontinuous moment in my life that sparked my path towards astrophysics. It's more like continuous series of events. I knew I was always interested in science in general and physics particularly. So whenever I used to get a chance, I used to go to these book fairs or maybe even some science planetariums, museums, and so on. And the interactions that I had with the curators and the other scientists in those places were definitely helpful, at least when I was in my preteens. So, yeah, so it's just a cumulative effect rather than a single spark, I think. But what I definitely knew was that since I was maybe 7 or 6 or 7, I knew I was interested in physics and the universe and how things worked, stars, and so on. I was definitely interested in it, and I'm just lucky that I was able to continue pursuing this as my career so far, thanks to many people.
I mean, it's interesting that you, I think, say something that I think will resonate with a lot of people working in this field, that it's cumulative, that there are
Yeah.
different paths that happen throughout that build up this interest rather than one moment that sparks it that I want to do this.
Yeah, yeah, including of course the teachers that I had during my middle school and high school. I used to pester them with what seemed to be very disturbing, not disturbing. They were disturbing to the classroom, but lots of questions. They may not. They could have easily dismissed me, but they did not dismiss me immediately. Instead, they took time to encourage more such questions. Such little gestures from teachers also played a huge role. I think I cannot, yeah, emphasize that more.
That's really nice to hear how when your teachers paved a path for that curiosity to grow and
Absolutely.
that they didn't dismiss those questions. And I would like to know a little bit more about your upbringing. For you, what do you think were those values or experiences from your early life that, for example, shape your work ethic or the way now you approach science?
I think it's really important to be honest with yourself. If you're doing science, that's a very important ethic that you have to have. If you do not understand something, it's very important to admit that this concept or something is beyond is something that we do not understand right now. I think that's the first step towards doing science. Only if we acknowledge that something is something can be we can be wrong about something, that some concept is currently beyond our understanding, would we even be able to make a first step towards understanding it. So having that sense of humility, right? So one should be willing to admit defeat. These are some qualities that I think are essential to be a scientist, because here we are trying to understand nature, and nature does not have to cooperate with all our ego, and that happens very often. We propose some theories and immediately we see observations that refute our theories, right? That happens very often, and it's important that at those times we recognize the deficiencies in our understanding, in our theory, to be able to come up with better ideas and better solutions. I think that is an important quality that is essential to be a scientist. I think growing up, my parents, for example, they definitely were not hesitant to point out the moments when I was wrong about something. They would not sugarcoat. They would plainly say that I was wrong when I was wrong. And I think, and my teachers too, of course, when I was in my school, although they encouraged curiosity driven questions, but when some of these ideas and questions that I came up with, or something that I was going towards, didn't make any sense, I had mentors, my parents and families and teachers, who did not sugarcoat, who told me things that they were as it is. I think that was probably helpful to have this, to develop this mentality towards science, I think.
No? Yeah. I mean, I think those are very important values that you raise up. I mean, I think the qualities of honesty and being humble are something that you're taught very early on as a child. But then I think Very interesting to see how much you say that it connects with you being a scientist and how important it is to follow or be very honest about the work that you're producing and that you don't know everything and you have to be accepting of the fact that you don't know everything. So you transition from growing up in India to studying and working in the US. For you, what were some of the cultural shifts that stood out to you, both inside and outside the world of academia?
I could give one example. So I did my undergrad in India, and then during the final year of my undergrad, I came to the US for the first time. I came to Caltech for a research project that became a part of my final year undergrad thesis. And the one stark difference that I noticed is being able to communicate science. So growing up in India, at least I did not have a lot of chance to give presentations and talks on my research activities. I did get a couple of chances, but I should not say I never had any chance. I did get a few chances, but when I moved to India, when I moved to the US, I had a newfound appreciation for science communication and how important that is. Especially when I had to give my first presentation, I bombed. I couldn't articulate well. I didn't know how to communicate my science well. I didn't know how to read my audience. It was almost a humiliating experience, to be honest. But that helped me to pay more attention to the way I communicate and communicate my research on science and how important that is in order to be in academia. And I found, on the other hand, undergrads in the US, they were communicating their science flawlessly. They're just flowing so smoothly. It was partly due to language barriers, sure. It was also partly the confidence with which people communicate, which I definitely lacked. That could be due to the language barriers, but also partly due to the ownership of the work that you do. At least in India, I don't think undergrads in general take ownership of the research that they do. They try to explore new research. They tend to do what they were asked to do typically, but I see a lot of ownership being taken by early career researchers also here in the US, which is a difference that I've observed. And taking ownership of the work that you do can also be really helpful in building up that confidence in the work that you're doing in while communicating the work that you did. So that's one cultural difference that I noticed in the scientific world, at least. And that's something that I would strongly encourage all early career researchers to take ownership of the work that they're doing. That can be really helpful for them to develop new ideas and to also communicate their ideas to others.
I think there is a very strong distinction that is there in India and the US, and especially how you grew from it. I think the piece of advice that you shared to any person when they are entering the field of academia or just starting in research, I think was be able to communicate that easily to an audience and be able to take ownership of that work, as you said. So, you earlier talked about the important role teachers had played in not only engaging curiosity but ingraining very important values and skills in you that helped you later as a scientist. So, do you recall any small or meaningful acts that a mentor or a teacher did for you? Something that left a lasting impact on your journey?
Many, the way I'm right now here, it's because of my mentors and teachers. Any small instance that I can particularly highlight. So the very act of not discouraging when someone comes up with genuine curiosity-driven questions that could be a very big boost for enthusiastic students, school students. And I was gifted with those teachers who did not dismiss my questions immediately. They chatted with me outside of class many times to lend a ear to some of my crazy questions and random ideas. And During my undergrad and PhD, some of my mentors, at some point, they decided to just let me be independent. And that is important, I think, to develop as an independent researcher. They would not spoon feed us at certain stage. Some of them, they decided, okay, I'm not going to spoon feed you anymore. And it was hard to make progress. That transition was hard, but that was a very important stage in my career, I would say. So yeah, I think these two instances occurred to me a few times during my undergrad, high school, and PhD. Although one of those instances can be immediately satisfying, so they are listening to our questions, they are answering our questions, uh, answering to our questions, which is really nice. And the other one, letting us explore by ourselves, can seem a bit we can feel a bit lost. But the second one can also be very valuable for you to charter your own path, for you to identify your own research interests. What doesn't immediately seem like a nice, satisfactory experience, and also on a long term, be really helpful. Those acts from my mentors, I would highlight those acts to be really helpful.
It's really interesting to see how your face lights up when you talk about your mentors and teachers. I think it's
Yeah.
evident how much of an important role they have played in your journey. And as you described the two parts, answering your questions with genuine interest and respect, but also giving you independence, not spoon feeding you at times, which allows you to make progress as well and learn. And I
The
think it's
progress would
really
be slower at first. It'd be harder to get your act together, but I think that's a very important step.
we know that your research dives into black holes, fast radio bursts, and other high energy astrophysical phenomena. How would you explain your work to someone completely unfamiliar with the field, say a curious middle schooler?
Yeah. So let me take one example, fast radio bursts that you just mentioned. So these are, as the name suggests, these are extremely fast events. They are seen through radio telescopes, and we believe they are some sort of bursty phenomenon. And these fast radio bursts are millisecond duration bursts that are mostly coming from outside of our galaxy, and they hit our Earth, several thousands of them a day, I think. And the amount of energy that they release in those that millisecond duration, very simply put, exceeds the energy that our sun radiates in 100 years combined. But because it's in radio band, we do not feel it. I would not feel fast radio bursts hitting us every day. We do not know what sources, what engine is powering these fast radio bursts. Until 2020, in April, we observed a fast radio burst coming from our own galaxy for the very first time. Until then, all the fast radio bursts were seen to be coming from outside of our galaxies. There were hundreds of ideas of what could be producing them. And then the FRB that we saw from our own galaxy, because it was coming from very close region, we were able to point all our telescopes, and then we were able to confirm that they were produced by these sources called magnetars. Magnetars are highly magnetized neutron stars. Neutron stars are the end stage of a massive star, a very massive star, say 10 times the solar mass or whatever, or 8 times the solar mass. It can evolve, and then it can explode into a supernova, and then it'll leave a condensed core behind, which will become a neutron star. And these neutron stars are extremely compact. They are just 20 kilometers in diameter, and they contain as much mass as our entire sun. So a teaspoonful of neutron star uh, weighs as much as the Himalayas or something like that. And these neutron stars have very strong magnetic field strength, 10 to the 12 Gauss, and these magnetars, 1,000 times even more, even stronger magnetic field strengths. And there are 30 or so such magnetars in our galaxy, identified ones, and one of those magnetars produced these FRBs. But we still do not know if all the cosmological FRBs coming from outside of our galaxy are produced by magnetars. I think there could be multiple engines that are producing FRBs. So even if we take magnetars as the engine for producing FRBs, we still do not understand the physical emission mechanism of FRBs. Okay, so you have a 20-kilometer diameter ball. How is it producing millisecond duration extremely energetic flares? We still do not understand. There are multiple theories. By emission mechanism here, I mean how are individual subatomic particles, how are they producing the radiation? How is the plasma around the magnetar producing these strong radiation? How is the magnetic field evolving? How is the magnetic field around the neutron star? This is a neutron star, for example, right? So these green lines that you see are imaginary magnetic field lines. And here you see some flare coming out of it. And this flare is due to the restructuring and reorganization of the magnetic field lines on the neutron star. How this happens is something that we do not understand, and we think some some flaring activity must be happening to produce FRBs, and how the particles like electrons, protons, and positrons, um, how they interact with the magnetic field lines to produce such an emission is something that we still do not understand. There are many theories, and there are many computer computer simulations, supercomputer simulations, but there is still no smoking gun evidence that from FRBs to say that okay, this is the emission mechanism, because each FRB has its own fingerprint. It's a bit different. So it doesn't seem like just one emission mechanism or one engine, like a neutron star or the emission mechanism, can explain all the FRBs that we have seen. So that's a very big problem in high energy astrophysics. And why is it important to study these FRBs? Like I said, most of these FRBs are coming from outside of our galaxy, from far, far away distances. And they traverse through a big chunk of our universe. So while they traverse through our universe, the universe also imprints certain properties of the matter of the universe onto the FRBs. So studying these FRB pulses and how they propagate through our universe can inform us a lot about how our universe evolves, how matter is spread across our universe, and so on. This is a new phenomenon. It has a lot of potential to inform us about our universe and explore new regimes of physics that cannot be replicated here on Earth in any laboratories.
Sounds very interesting, and I mean, I would like to ask a question: Is do you think FRBs that repeat give much more insight than discovering, for example, more FRBs that are not repeater candidates with just one-time events?
Yeah, that's a good question. One thing that I did not touch upon is the host of FRBs. I was talking about the engine of FRBs, neutron stars, or potentially black holes. That's something that I worked on, and the emission mechanisms, the microphysics of it. But I did not mention the host of FRBs, the host galaxy, or the galaxy that is that is host to the engine producing FRBs. One-off events, it's hard to localize them. But if you have a source, if you can point a region in the sky that is producing multiple FRBs, then you can focus your facilities to observe that region much more deeply, to point out what could be the nature of the galaxy that is producing the FRB. That is only possible when we can localize the FRB, which is only possible if you know that this source is producing multiple FRBs. So repeating FRBs have opened this new field of galaxy or host localizations of FRBs. And that is very important because certain galaxies are known to be producing stars more frequently. Certain galaxies are not very active with star formation, and so on. So different morphology of galaxies are known to host different transients like gamma ray bursts or tidal disruption events. These are different explosive phenomena happening in our universe, which preferentially occur in certain types of galaxies. So if we can say that, okay, fast radio bursts preferentially occur in galaxies that produce a lot of stars that are very massive and so on, that information can be used to compare the properties of FRBs against other transients to pin down what could be the progenitor engine that's producing these transient signals. That's just one example of how repeating FRBs can be helpful to understand them better. But that said, repeating there's a really well defined dichotomy between between the properties of repeating FRBs and non-repeating FRBs. So it's not immediately clear whether understanding repeating FRBs really well also informs us everything about non-repeating FRBs. They could potentially be different populations. So at the same time, most of the non-repeating FRBs or not yet seen to be repeating FRBs could repeat in the future. It's unclear. But repeating FRBs can help somehow, but I don't think uh, they will solve the mystery entirely.
I mean, this entire topic sounds so fascinating, especially the mystery of FRBs, and it was very insightful to hear about your explanation of the topic. And I'm sure a middle schooler watching it will be able to understand what they are and hopefully go ahead and research more about what they are. Moving beyond FRPs, I feel there's a perception in astrophysics that people feel it's all about beautiful telescope images and space visuals, and I mean, there's a lot more that goes on behind the scenes. So, what do you think is something a little unglamorous or behind the scenes that people may not realize is central to your day-to-day work as a researcher?
Yeah. To be honest, I never got into this field because of the beautiful images. I do not use telescopes anymore. I mostly code and solve problems using computers. You just have to be good with some numerical skills and some physics, of course. It's going to be something that involves actively looking at these explosions in real time, and there'll be beautiful images and videos. It's not really the case most of the time. No. In my case, I just sit around and scribble in the notepad some equations and whatnot, and then try to understand some phenomenon that observers report. And many times the code does not run. Most of your time, you just keep debugging your code. Your analysis routines are the numerical simulations that you submit to a supercomputer. Um, that's where you spend most of your time, and then most of the time is just doing unglamorous stuff. And eventually when your idea or when your theory matches some observations, which occurs rarely, you get to enjoy that moment for a while. Until then, it's debugging, coding, scribbling down some equations, and that's it. That's how it works. It's fun to me. It's fun to me, solving any kind of problem, including the numerical ones and the physics equations. They're all fun. But if that's not the idea of fun for anyone, then this may not be the right track for them.
I mean, it sounds a lot like detective work,
Yeah,
where you're
yeah,
trying to piece together clues and build a puzzle together, solve a
yeah.
puzzle.
Yeah, that's one beautiful thing about astrophysics, right? So this is one field where you get to use all physics concepts from condensed matter physics or quantum mechanics or optics, different kinds of optics, emission mechanisms, plasma physics, QED, quantum electrodynamics, or general relativity, plane mechanics, classical mechanics, and so on. So this is a field that lets you be in touch with a wide range of physical concepts, and that can be fun. So you use all these tools that physics offers. You get to use all these tools that physics offers to understand something that other fields, unlike many other fields.
I think that's what makes this science so interesting, that it's not very limited to one aspect of
Exactly.
the science, but you get
Yeah.
to explore and use and learn so many different things and use that together in your work.
Yeah.
So you've been involved in teaching complex astrophysics concept and you explain it so well. So what's your approach to making these ideas more accessible to students or the public?
I think the first thing is to not assume that everyone in your audience is at the same level, that they all have the same background. So it's important to be able to cater for the students or the audience member with the least background. At the same time, you don't want to lose the interests of people who have some more experience too. So it's a balancing game. I don't think that's easy, but one way to go about it is basically to not use a lot of technical jargons, at the same time being able to challenge one by using simpler words, challenge a person's perception about something using simpler words. I think that's a way to communicate science to the public so that you don't lose a part of your audience.
What do you think is the best part of being an astrophysicist?
There are a couple of parts, right? One is being able to say two or three parts. One is being able to learn new things. The other one is being able to encounter new problems and just approach new problems, and the excitement that you get when you know you solve a problem that happens ever so frequently in astrophysics. And the other one being new surprises, right? So every single day you hear an astronomer's telegram or some new papers coming out that are extremely surprising, some new events that happen. And if you are generally a curious person, then this can be a very fruitful experience because there's always some food for for your curiosity, some way to keep you curious about the universe. For example, once I was, I think the April 2020, right? I was in India during COVID. I just had come to India. And then we heard a news. Local magnetar has produced an FRB. So that was a huge discovery. And within a week or so, I was in India, and then I had a few collaborators in the US and other places. Around the clock, we were working to understand the phenomenon, and we published a paper on that. So such instances, such events that the universe present happens. When it happens, it can be really exciting. Yeah, newer problems are always fun.
I think that's a very nice note to end it on. I mean, it's really incredible to see the excitement with which you talk about the subject and your excitement to learn new things at all times in this. Thank you so much, Dr. Naveen, for taking out the time to talk to me. A lot of fun talking to you and hearing about your work, about your journey entering this field, especially the favorite parts. As you say, there's not one, but there are many different parts that make it as interesting so that it doesn't feel like work, that it's fun for you. Thank you.
Yeah, thank you so much, and yeah, good luck.
Thank you so much for watching till the end. We've learned not just about fast radio bursts from Dr. Naveen, but so much more about his journey and the trademark secrets of a successful and passionate astrophysicist. Hope to see you next time.